Okay, this problem is a catapult is used by knights and hurls a stone with a mass of 32 kilograms with a velocity of 50 meters per second at a 30-degree angle of elevation. A. What is the maximum height reached by the stone? B. What is its range, defined as the horizontal distance traveled when the stone returns to its original height? And C. How long has the stone been in the air when it returns to its original height? So the first thing I started when I started doing this problem was I drew this picture of what's going on, and the catapult right here hurls a stone going towards the castle, and it is in a horizontal an upward direction with a degrees of 30 degrees. And so we're going to do question A first. So our formulas for the initial velocity in the y direction is the initial velocity times sine theta, and then we have our initial velocity in the x direction equals the initial velocity times cosine theta. So then we have the max height is equal to the it's going to be the vertical displacement and the change in y when the final velocity in y is equal to 0, and that's our formula right here, which is change in y, which is equal to 1/2 final velocity of y plus the initial velocity in y, which is change in time, is equal to 1/2, and then we plug our vinyls in for that, and is equal to 1/2 0 plus initial velocity times sine of theta times change in time. I couldn't fit it right there. But then we can go on ahead and eliminate the time interval by using the formula underneath it. Reading the final velocity of y minus the initial velocity of y is equal to the acceleration of y times the change of time. And using that, we get this formula right here, which reads the change in y is equal to 1/2 times the initial sine of angle theta times 0 minus its initial velocity sine theta divided by the acceleration of y is equal to the negative initial velocity times sine theta squared divided by acceleration in the y direction times 2. So then we plug our volumes in for this, and we get that the maximum height of the projectile is 31.9 meters above its launch height. Now, I decided to do C before we do part B because it's just easier to find the ranges quickly. So the initial and final is the same. So you do this symmetry at time of the flight is twice that it takes the projectile to reach its maximum height. So we can find the time to reach its maximum height by the formula right here, which is the final velocity in the y direction is equal to 0, which is equal to the initial velocity in the y direction plus acceleration of y times the change in time. So then we solve for the change in time, which gives you the negative initial velocity divided by acceleration in the y direction. So then the time of flight is our formula right there, which is the final time. The change in time times 2 equals 2 times negative 50 meters per second times sine of angle 30 degrees divided by 9.8 meters squared, and that gives us 5.1 seconds, I'm sorry. So then we jump back to part B, which is right here, which is what I did last. To find the range, we just use our formula from the change in x is equal to the initial velocity in the x direction times the final time, and we plug our values in, and we get 50 meters per second times cosine of angle 30 degrees times 5.1 seconds, and we get 221 meters, and that is how you find that.